Hello everyone, welcome to the next lab of EC 573 Advanced Embedded Logic Design. In this lab, we are going to discuss about the design of the FIR filter, its implementation on the processor as well as on the FPGA. So let's start with the basic understanding about the FIR filter. So FIR stands for Finite Impulse Response Filter. So in this case, FIR filter is defined by the set of filter weights. Okay, so we can assume that the FIR filter is of the order L, or if the filter length is L, so that means there are L number of filter coefficients. Depending upon the type of the filter, sometimes the filter coefficients are symmetric, sometimes they are non-symmetric as well. So for example, linear phase FIR filter, they will always have the symmetric filter coefficients. Now, in case of the FIR filter, ideally you receive the input sample by sample and you produce the output sample by sample. So for every input sample, you produce the one output sample. So assuming that right now the input sample is say x of t. So for the x of t, you will provide the output sample which is y of t. And this y of t is obtained by the convolution operation between your input current as well as previous input. Okay, so it should be current and previous input and the filter weight. So convolution between the input and the corresponding filter weights. Okay, so for example, you have the output which is y of t at time t. It is performed using the convolution of size L. So there will be L Mac operation. So I is equal to 0 to L minus 1. And you will have the W of I. So each filter width you will multiply with the corresponding input. Okay. So you will have the filter width 0 with the corresponding input, filter width 1 with the corresponding input, and so on. So for example, here you can write x of t with the here you can have the L minus I. So what does it mean? So here when you have the W0, you will multiply with the x of L. Okay, that is the so sorry, it should be the T minus I. Okay, so here it indicates that you are going to multiply the W of 0 with the current input. Okay, plus W of 1 with the previous input which was received in the previous clock cycle or previous time slot, plus W of 2 into the input which you received before that T minus 1 input, and so on with the W of L minus 1 into x of T minus L plus 1. So basically your current output at the time t depends upon the current input as well as the past L minus 1 input. Okay, so this is the filter design. So now graphically how it looks like. So you have the shift registers. So assume that I'm considering the filter of length 5. So there will be 5 MAC operation. Okay. So this is the shift register. I need a shift register because I need to store the past input. Then this is your input. So you can say that this is, this is my x of t, this becomes x of t minus 1, this becomes x of t minus 2, x of t minus 3, x of t minus 4. And then you will be doing the multiplication. So you have the multiplication operation here. So since this is the filter of order 5, okay, so filter of order 5, and that means length is 6. You need 5 multiplication operation, and then you will perform the addition operation here. To get the y of t. Okay. So you can see that when you apply the x of t, you get the y of t, and y of t, you can see that the x of t, then you have the w of 0, w of 1, w of 2, w of 3, and w of 4. So this is how your filter looks like. Now, there are multiple ways of implementing the filter. One is that you can implement the filter in the parallel fashion. What do you mean by parallel fashion? That means you perform all those multiplication addition in parallel, so that you can have the initiation interval of 1, so that you can get the output in the same clock cycle or in the next clock cycle as fast as possible by performing all the MAC operation in one clock cycle or in parallel. Then the serial filter. In the serial filter, you use only one multiplier, and then you do this operation in the sequentially. So this is the serial way. And you can see that the serial, you will need less resources, but it will be slower. Parallel, you need more resources, but it will be faster in execution. Then another thing is, in addition to the MAC operation, you need a shift register to store the previous values of the input. So these are the things you need to look at. Now suppose that the filter coefficients are symmetric. What do you mean by symmetric? In that case, W0 is equal to W4, W1 is equal to W3, and then you have the W2. So in that case, you can see that since this W0 is same as W4, you don't need to do the two multiplication operation. What you can do is that you can perform the addition of these inputs, and then you do the common multiplication. Okay. So if you want to look at the architecture, suppose I have the symmetric filter coefficients. So in that case, I'll have the z to the power minus 1, then z to the power minus 1, z to the power minus 1. I need only fewer MAC operation. So I'll have the first addition here. Okay. So this addition will be this input. Okay. And you can see that what I'm going to do is that I'm going to have the z to the power minus 1 and z to the power minus 1. Then I'm going to do the add operation here. Then I'm going to do the multiplication operation with the w of 0. Here also multiplication with the w of 1, multiplication with the w of 2. And this is addition, and then I get the y of t. So here you can see that I'll do the addition here, and then I'll do the addition here. And for this one, okay, so I got this one covered, this one covered, and I don't need any adder here. So I can remove this adder. Okay, so I think I have made a mistake here. This was not necessary. Yeah, so I have this here, then output of this will be here, and this is the conventional. So you can see that instead of having this multiplier, I added this output with this one to get, since I know that the W0 and W4 are same. And similarly, I added this with this one since W1 and W3 are same. So I get a better, more efficient architecture. So this is called as a symmetric FIR filter with the symmetric filter coefficient. So by exploiting this symmetric architecture, you can see that we will be able to get the lower resource utilization. Now, what we are going to do in this lab is that first we are going to create a HLS IP for filter. We are going to create 3 HLS IP. One is for the serial, one is for the parallel filter, and one is for the symmetric parallel filter. Then we are going to use the second thing is that we are going to use the DMA in the scatter gathered mode, and we are going to do the comparison with the FIR filter in the PS, FIR filter serial, then parallel, and then FIR filter with the symmetric parallel. For the time being, I'm keeping the word length as integer, but you can later explore the other fixed point word length or the integer also. You can reduce the word length from 32-bit to lower depending upon your application requirement. Right now, I'll not focus on the word length. I'll focus on the different filter design. Okay, so now what we will do, we will now move to the HLS IP creation, and we'll look into the corresponding HLS code. Okay, so this is the HLS code. So you can, I have the .h file where I need to define the stream interface. So I have defined the corresponding structure where my data type is of the type integer. Now here I have defined the one variable called sample that indicates the size of the data packets to be filtered. So I'll receive the input data of size 512 samples. I'll filter those 512 samples to get the 512 samples at the output. And here I'm mentioning that the range is from 0 to 15 integer value, though I'm not going any word length optimization. I have defined the filter as the 51 tab filter. That length of the filter is 51, so the corresponding coefficient. And these coefficients are defined as a symmetric coefficient. Again, you can modify this code to input the filter coefficient from the user via another stream interface. So that is also possible. Then I have 3 solutions, one for the normal FIR filter in parallel. Second is the FIR filter, which will work only when the filter coefficients are symmetric, and then the serial implementation of the FIR filter. Now let's look at the code. So the first filter is the normal FIR filter, which can work for the symmetric as well as non-symmetric filter coefficient because it is the normal convolution operation. So I have received I have made the interface as a stream interface. I have received the data over stream and I converted into the normal vectorized input of size samples. Okay, so I receive this input. Then I have the for loop, which will process one input at a time, because in the FIR filter, you can give only one sample at a time as an input. Then I have 2 for loop. Here I have the one for loop. In this for loop, I'm doing the shift operation because whenever I receive the new input, I need to shift the data inside the shift register. So I'm doing the shift operation. I am doing the accumulation operation, the MAC operation, multiply and accumulate operation. Okay, so I'll do this for the data which is already present in the FIR filter. And then for the new sample which I have received, I perform the multiplication with the corresponding filter input. That is the first filter coefficient. And then I'll put that, I'll insert that input inside my shift register. Okay, so this is the very simple code for the FIR filter, and I get the output. Then output data, which is the vectorized data, I'll convert into the stream form and I'll return it. So this is the normal FIR filter, which works for the symmetric and non-symmetric filter. Then I modified this code for the symmetric one. Before discussing the modification, I have done the small optimization. In the small optimization, what I have done is that I've just done the pipelining of the upper for loop, so that I want to receive the new input sample at every clock cycle. So in that case, this operation, which is the shift register operation, and the MAC operation will be done in parallel, because that loop gets unrolled. So for that, I need to break down this shift register into the so that I can access all the elements in parallel. So I did the array partitioning, and for the MAC operation, I'll use all the multiplication will be done in the parallel fashion. Okay, so this is how I have received the data. Now, in the solution 2, here what I am doing is that in the solution 2, I'm just trying to exploit the symmetric filter coefficient. So if the filter coefficients are symmetric, then what I need to do is that I need to reduce the number of multiplication. So I have broken down the loop into the two part. One is the shift register part, because shift register still will happen. Size of the shift register will not change. It will happen in the it will size is equal to the number of taps, because I need to store all those previous input, but the size of the MAC operation will be reduced by half. So this is how I have done the corresponding logic. You can have a look at it later and then understand it. Rest of the things remains the same. In the serial filter, again, in the serial filter, I am going to perform the operations in serial fashion. So I don't do the pipelining here. I do the pipelining here, so that I can do the shift and the MAC operation as fast as possible. So here you can see that since this loop is not pipeline, this loop will not be unrolled. So you are going to do the one multiplication at a time, in this case of the serial filter. So here you might wonder, in all the three I have done the partitioning for only the shift register. So you might wonder why I have not done the partitioning for the local FIR input array. This is not necessary, because as I told you before, the filter input is you are going to receive only one sample at a time, and you are going to produce only one sample at a time. So that means there is no need of partitioning this input and the output array, which is the local input and output array. So you need to understand that you can't do the partitioning blindly. You need to understand the logic and the architecture to know which part to be partitioned and which part should not be partitioned. And the code will work even if you partition the FIR, local FIR input as well as local FIR output, but you will not see any gain in the execution time. Only your resource utilization will be significantly increases. So now for this filter, where I am not exploiting the symmetry, you can see that I have 3 for loop. I was able to meet the initiation interval of 1 for the first one, because there I am doing only the receiving the data. In the second one, since I am going to perform the write operation, the initiation iteration latency is high, but initiation interval is 1. That is the best I can do. And where I'm doing the MAC operation in parallel, you can see that my iteration latency is 5, but initiation interval is 1. So this is the best we can do. And you can see that the resource utilization is around 3K flip-flop and around 3.3K LUT. So now what we do in the second solution, we try to exploit the symmetry. Now by exploiting the symmetry, you can see that what you are going to achieve is that you are going to reduce your resource utilization, because the number of multipliers are reduced by significantly. And you can see that now is your flip-flop utilization as well as the lookup table utilization has reduced. Okay, so that is the advantage you get by using the symmetric filter. Okay, so the third solution is the serial FIR filter, and you can see that and the latency is significantly higher because it performs the operation serially. but you can see that the resource utilization is much lower, only 2K flip-flop on only 1K lookup table. So that's a trade-off. In the serial FIR filter, you perform the operation in serially, but that's why you get a high latency, but you get a lower resource utilization. You can do other combination also, serial parallel. You can do some operation or bunch of operation in parallel, and then do the operation in the serial parallel fashion. For example, there are 51 MAC operations, so you can do as a 10 10 10 10 10 and then one operation, or you can do various other you can do the 17 17 17 as a serial parallel fashion, depending upon your resource and the your latency requirement. Now these three IPs are now created. After the IPs are created, they are exported to the Vivado, and now we will see a look at we'll look at the corresponding block diagram. So you can see that I have the three filter coefficients, three filter, FIR serial, FIR parallel, and FIR the symmetric one. And then I have used the 3 DMA in the scatter gathered mode. So they are connected to the DDR memory via ACP port, and then I'll configure them in the SDK code. So the block diagram is more or less similar to our previous lab. So make sure that you export the IP properly from the HLS. Ideally, you should see this HLS symbol here also, but since I have modified something in the HLS, so that's why I need to refresh the IP catalog to get the updated data. But right now I won't do it because otherwise I have to generate the bitstream again. So after this, I'll export the hardware to export the data to the SDK, and then I'll write the application code in the SDK. Okay, so SDK, again, the project and the code is more or less similar to the previous code. Here we are going to do say 3 experiments. You can increase the number of experiments. Instead of the mat data type in the previous matrix multiplication, we are using the FIR data type. Again, it's integer. Packet size is 512 and the filter length is 51. Make sure that this remains the same as your HLS IP, and this coefficients remain same as the HLS IP. Then quickly looking at the main code to understand what we are going to do. What we are going to do is that we are going to call this function 3 times, and we are going to pass the corresponding input 1, 2, 3. 1 indicate that we are going to run the FIR filter on the processor, and we are going to enable the DMA which is connected to the FIR filter, which is implemented in the serial fashion. Then we will call it again 2. In this case, we are going to just implement the FIR filter in the, we are going to call the DMA, which is connected to the FIR LP, where it is implementing the FIR filter in parallel, which is for symmetric as well as non-symmetric. And in the third case, we are going to call the IP, which implement the FIR filter only for the symmetric coefficient. And for all these things, we assume that the filter coefficients are symmetric. So we are going to call the same function 3 times. So if you go to the quickly in this 3 function, it is more or less same. Depending upon the choice, what we are going to do is that we are going to configure the corresponding DMA 1. So you can see that depending upon the choice which we received, we are going to call the corresponding DMA. Then we are going to configure the DMA. We are going to do the TX setup and RX setup, which is remain the same. Then only when the choice is 1, we are going to create the input so that the input remain the same for all the letter calls. So that's why we have defined this as a global variable. Then we are going to implement the FIR filtering on the processor only when the choice is 1, that is the first time. And we are going to keep the data serial data ready for the DMA. So this part will be executed only when the first time. Then the next thing is set of creating the buffer descriptor and updating the buffer descriptor, that remains the same for the EXPT number of times. And then we are going to call the corresponding DMA, passing the buffer descriptor to the DMA, and so on. The things remain the same. Okay. And depending upon choice, we are going to find out the corresponding execution time. Okay. So the code is more or less same way of the previous lab, where we are going to compare the here FIR filter on the processor, serial FIR filter, parallel FIR filter, and the symmetric parallel FIR filter. And the benchmark function is same, RX setup and TX setup functions are same. Now we will quickly test this design on the hardware. So here I have connected to my remote hardware. I'm using the Zedboard, which is remotely connected. So that's why I'm using the debug mode so that I can see the output on the UART. So I'll just quickly run the entire code. And you can see that I got the execution time for 3 experiment. The processor took 3820 microsecond. It is the significantly higher microsecond because MAC operation means multiply and accumulation operation, which takes a lot of time on the processor. On the FPGA, you can see that this even the serial mode with including the data communication, it took only 310 microsecond. On the parallel one, you can see that you got significant improvement. And parallel symmetric, you say that you don't get this improvement as such. It's more or less same, but you get less resources in the parallel symmetric. Now what we'll do is that we will just run the code step by step to understand what happens in every step of the um, code. Okay, so you can see that the first time here I'm calling this function and then I'm making the choice is equal to 1. Then choice is equal to 1 means it will be implementing the FIR filter on the processor. It will be creating the data ready for the DMA input, and then it will be calling the DMA which is connected to the serial HLS IP. So if I run this now, so you can see that I got the this time for the serial FIR IP. Then when I call the function again, so you can see that when I call this function again, so I'll run to this line. Now the choice is 2. So what it will do, it will configure the DMA which is connected to the parallel FIR filter. So you can see that the code will come here. Okay, so now that DMA gets configured, this part that the implementation on the processor is not needed because I have already created the reference output, which is a global variable. It is already been created, and the corresponding input I have already created. This is the global input, so I don't need to regenerate this one for every filter. Now this DMA will take this DMA input, pass it to the HLS IP. It will get the DMA output, and this will be compared with the same benchmark output which was generated in the first call. So that process will happen, and the same process will happen in the when you call this function again with the input as a 3. In the third case, it will call the DMA which is the connected to the symmetric parallel FIR filter. Okay, so this is how you can implement it, your FIR filter. So now you can see that we were able to implement the filter in the multiple ways. Now few modification you can do is that you can do the compiler optimization to improve the speed up on the ARM processor. Then you can analyze the throughput or perform execution time you get for the different size of the experiment. Also, here in this case, you can see that the FIR filter is fixed coefficient FIR filter. So when the coefficients are not fixed, how you can uh, add another input via stream interface for inputting the filter coefficient also. Also, in this case, you can see that the your FIR filter length is also fixed. When the filter length is not fixed, how to design the corresponding FIR filter? Those are the things you need to look into the account. Then sometimes you need to do the interpolation decimation, how you can incorporate that functionality. So these are the things you can incorporate in your HLS IP to meet your application requirement. But the basic structure of the FIR filter will remain the same. Another thing you can look at is that word length optimization, how you can optimize your word length to further reduce the resource utilization that you can have, you can explore. Okay, with this, we have completed our lab where we have analyzed the performance of the FIR filter on the Zinc SOC.